Okay, so this mini lecture is probably on my most favorite topic in the world of E&M. And it is related to the discovery, or it is the discovery of two amazing scientists who looked at and started to question this idea of, well, if current can get a magnetic field, if a current can produce a magnetic field, can a magnetic field produce a current? And the thought really was, well, if they're so interconnected, and we believe they're at the time they were so interconnected, so many people were looking at this question because, of course, current. If we could generate current, wouldn't that be great, right? All of our energy, for example. So there wasn't any real evidence that if there was a conductive element like a wire or a conductive loop, something that a current could flow through, that just having it in the presence of a magnetic field caused a current to be induced. Well, the short of it though is, yes, it can-ish. So it turns out that if you have a conductor in a magnetic field and you change the magnetic field, then we get a current induced. So it wasn't that the conductor had to be in the presence of a magnetic field. Instead, the magnetic field had to change relative to that conductor. We're going to get into a little bit more detail. So the gentleman who really discovered this phenomenon was a gentleman named Faraday. And he found that what matters is the amount of magnetic flux that goes through a coil in a wire. So how did you discover that? Well, imagine you have a loop of wire and you have a bar magnet. And when you put the bar magnet inside the wire and kind of just left it there, nothing happened. But he noticed that as he was moving the magnet in and out of the wire, a current was actually induced in the wire. So when the magnet moved in or out of the wire, a current was induced. But if it was stationary, then there was no current. Okay? So he started then to think about, okay, well, what is going to influence the amount of current I might get? So he first discovers that the magnetic field has to change in relation to the conductive loop. Okay, so that is what became important. The magnetic field had to change in relationship to the conductive loop. Now, what was discovered is that it's not so much about the magnetic field, but the magnetic flux. Now, we've already talked about this word flux before. We talked about an electric flux in terms of Gauss's law. How much of the electric field passes through an area, right? How much of the electric field passes through an area? That was our idea of Gauss's law. Well, the magnetic flux is the same idea. How much of a magnetic field is passing through the area? And just like with Gauss's law, the magnetic flux is related to the line integral of the magnetic field dot dA, where, remember, that area vector, make these two vectors just as to remind us that those are vectors, that area vector was the vector perpendicular to the cross-sectional area of the surface that the flux is going through. Okay, so if you don't quite remember that whole kind of description of electric flux, I encourage you to go back and look at that mini lecture on electric flux. So it's the flux that's important, which gives us a couple of things, right? Not only is the strength of the magnetic field important for the flux, but the area that magnetic field is going through is going to be important for the flux and thereby important for the amount of current induced. Now, the other piece that's important that Faraday discovered is not only is it the flux, but it is the rate of change of the flux. So if he were to move the magnet slowly into the coil of wire, we certainly get a current. We get a larger current if we move that magnet quickly into the coil of wire. So what Faraday's law tells us is that the current induced, which results in an EMF, is related to the change in flux per time through the loop. Okay, so that current induced results sort of in this EMF, right? This voltage difference is our change in flux per time. So we get a current to flow. Now this relationship is for a single loop of wire. So a single loop. If I add more loops, then I'm kind of adding up the flux through each one of those loops. And we find that in general, N is equal to the number of loops. The EMF, kind of make that curve. Those are really lots of squiggles there. That kind of curly QE. Our EMF that's generated, this is Faraday's law. Oh my goodness. So what do I want you to know about this law? Basically, that current can be induced with the aid of a magnetic field as long as that magnetic field is moving relative to the coil of wire. And what's most important about that is that that magnetic field is moving in such a way that the magnetic flux is what's actually changing. So the angle that that wire is within the magnetic field is going to be important, because if the magnetic field is in line with the coil of wires, we're not going to get a flux we're not going to have an area that has a perpendicular component to get a flux, right? So it is the flux as time goes on, so how fast, the rate of change of that flux in a coil of wire, and the number of coils increases. Now, why do we care about this? Why do I think it's so cool? Well, it turns out that it is Faraday's law that allowed me to get my PhD. So I studied neuroscience, as I've shared with you, and I studied eye movements, and I used human subjects as my eye movement subjects. And we needed to understand eye movements at a very, very, very sensitive level. So what did we do? We took a coil of wire, just a coil of wire, did not put anything in it, didn't connect it to a voltage source or anything, and I popped it on the eye, kind of like a contact lens. And then I put my subjects into an external magnetic field, and I changed that magnetic field when I wanted to calibrate. Okay, so I wanted to normalize the coil of the current in the coil of wire. And then I put them in that steady magnetic field, and when their eye moved, the coil of wire moved. And it changed its angle, thereby changing its flux, because the area vector of that coil of wire changed. I got different fluxes through that coil of wire, inducing a current, tiny little current in that coil of wire, and it was allowed me to measure with the high sensitivity and high precision exactly how much the eyeball rotated. So that was super cool. So I credit my PhD to Faraday, so he holds a very special place in my heart. Now, you might have also seen other uses of Faraday's law, one of which is induction stoves. So if you've ever seen an induction stove, it's one where you can put your hand on the heating element, and you can boil a pot of water right next to your hand. Perhaps you've seen pictures of that. I believe there's a picture of that. In fact, I know there's a picture of that in your textbook. But a good friend of mine had an induction stove. Now, you need a special pot. How does it work? Well, the heating element is actually a coil of wire that a current is put through, AC current, what comes out of our outlet, right? AC current, alternating current, and that coil of wire then induces a magnetic field, right? Current carrying wire causes a magnetic field. So then I put a pot on top of that, and that pot has a ring of conductive material. So that alternating magnetic field causes a flux that changes through the pot. And because that pot has some resistance, the current experiences some resistance. That potential that's set up has some resistance, so that current flows, and the energy transferred through because of that resistance is in heat. And so the pot heats up, even though the actual heating element is not hot. Other ways that we use Faraday's law are in things like windmills. In windmills, inside and generators. Inside the windmill, you can imagine that there's a giant magnet. So here's a uniform magnetic field inside the windmill. And I have a shaft and a coil of wire at the bottom. And as the windmill spins in the air, this coil of wire starts to spin, thereby getting a change in magnetic field in that coil of wire, and a current is induced. And then they have to do some modifications because it's spinning in one direction and in and out and all that. We're not going to worry about that, but the point is, that's how we harness energy from the wind, electrical energy from the wind. So Faraday has provided us with some pretty awesome, not just my PhD, but pretty awesome tools utilizing this idea of an induced current in an alternating or changing magnetic field, a changing flux. Now, as the title of the lecture shows, there's another scientist who is also very interested in this idea. And it expanded on Faraday's law. Let's go back and kind of remind ourselves that if I induce a magnetic field because I have a current carrying wire, a magnetic field is induced. And then I have another wire next to that magnetic field. Well, we know that, and that magnetic field is changing. Faraday's law induces a current in a conductor. Let's just say a wire, coil of wire. Well, that coil of wire now has a current in it. And we know that the current causes a magnetic field. So now I have two magnetic fields going on, all right? Well, Lenz has discovered that the induced EMF causes a current in the direction that counters the magnetic field. Meaning, the magnetic field that is the result of the induced current opposes the external magnetic field that caused the current. Okay, so we're going to talk about two magnetic fields. Because, again, if I have a coil of wire and I put it in an alternating magnetic field, a field whose flux is changing, I induce a current in the wire, Faraday's law. The current in that wire, because it's a current carrying wire, causes a magnetic field. Lenz's law tells us that the current is set up such that the induced magnetic field opposes the magnetic field that caused the induction. That's a tongue twister. Let's look at an example. All right. So let's imagine, I think this should clear it up, that we have a magnetic field pointing out of the page. Okay, so that's a magnetic field pointing out of the page. It's uniform magnetic field. And I have this loop of wire, okay? And I'm going to, let me change the color of that. I have this loop of wire, and if I just sit that there in the magnetic field, nothing happens. It's nothing. There's a flux through that loop of wire, right? But nothing is happening. And now I take this loop of wire and I move it with some velocity to the right. Okay, now this is the edge. It's important to note in this image that this is the edge of the magnetic field. So as soon as my loop of wire moves out past this line here, it's not experiencing a magnetic field. There's no flux through that part that's external to that line or to the right of that line. So what happens? As I move this coil to the right, as I move that coil to the right, the flux through that coil decreases. The flux through that coil decreases. It's a change in flux, which implies a current is induced in that wire. Okay, current is induced in that wire. What's the direction of that current? That's when we look at Lenz's law. Lenz's law tells us that the magnetic field, this induced current, will produce a magnetic field that opposes the flux. Okay? So, our flux is decreasing. Our flux is decreasing. And we want to oppose that, which means we want to put more magnetic field lines through the loop to oppose the decreasing flux. All right? So as I move this current loop to the right, you're going to use your right hand again, that's a little goofy with the light board, but I need my thumb to point in the same direction as the external magnetic field. So I add field lines as I decrease the flux externally. I'm adding field lines through the induced current. I'm opposing it. So in this example, the current will flow which direction? It'll flow counterclockwise. A counterclockwise current will have the current flowing out of the page, the magnetic field flowing out of the page. That magnetic field out of the page adds magnetic flux through. Imagine it's adding kind of magnetic flux through that loop, countering the decrease in the magnetic flux. That's Lenz's law. Okay? It's kind of this fun little logic puzzle. Let's do another one. All right. What if I have a magnetic field? So let's say I have a magnetic field going into the board. So here's my magnetic field. And I have a loop. Here's my loop. And I shrink the loop. Shrink the loop. Okay. With a shrinking loop, am I changing the flux? Yeah, my area is shrinking. So I'm changing the flux. I'm going to induce a current. Okay. How am I changing that flux? I'm decreasing the flux through that circle. I'm decreasing the flux through that circle. Therefore, the induced current has to be done in such a way that I will oppose that decrease. So if my magnetic field is going into the board, and it's decreasing in flux, I need to add more field lines into the board to oppose that decrease. That means my thumb has to point into the board, and my current is clockwise. All right, so these are kind of fun. So the idea, again, is that Faraday's law tells us a EMF, a current, and a current, is induced in a conducting loop, when the magnetic flux changes as a function of time through that loop. Lenz's law tells us that the magnetic field generated by that induced current opposes the magnetic field that induced the current. All right, I'm going to kind of play with the puzzle. So, conceptual here, we're just going to look at this conceptually in this little mini lecture in this part of our exploration of E&M. Super fun. Near and dear to my heart, of course. Great job.